In this video lesson, we're going to talk about the concept of work. Work is going to be the last set of notes that we talk about for Unit 7. In this video lesson, we're going to define what work is, we're going to be able to calculate work, and we're also going to define and calculate using the work-energy theorem. So let's go ahead and get started. Let's first start out by talking about what work is. Work is defined as being energy transferred that's through a displacement process. So the key thing to note here is that work is just simply an energy transfer, which is what we've actually been dealing with all along. Specifically, displacement is what needs to happen. If displacement is not happening, or in other words, if an object is not moving its position, then work is not being done. More specifically, there are three ingredients that you need to have in order for work to be done. The first one is force, the second one is displacement, and the third one is cause. So once again, in order for there to be work, you need to have a force, you need to have a displacement, and then what that third point means is that this force must cause this displacement. So let's look at some examples so we can understand what this means. All right, let's imagine a person is applying a force to a wall and becomes exhausted. So you're pushing a wall, trying to make it move with your brute strength. Even though you are applying a force to the wall does not change its position. It doesn't displace. And so there would be no work in the first example. All right, in the second example, a book falls off of a table and free falls to the ground. Is there a force? Yes, there's force gravity. Is there a displacement? Yes, the book clearly changes its position from the top of the table heading towards the ground. The final step, the third check, is the force of gravity what's causing the displacement? And the answer is yes. The force of gravity is actually making it fall vertically to the ground. And so yes, work is done in the second example. In the third example, a waiter is carrying a tray full of meals above his head by one arm straight across the room at constant speed. All right, so to kind of visualize this one, imagine that a waiter's hand, and I don't have very good drawing skills, but a waiter's hand is like that, and is holding a tray of food like this. The waiter is applying a force applied upwards. And as the waiter moves across the room, the tray is displacing horizontally. Is there a force? Yes, force applied. Is there a displacement? Yes, it is moving across the room. Is this force applied going up and causing the displacement across the room? No. And so even though there's a force and a displacement, they are not causing one another. And so there is no work done by the waiter's hand. Finally, a rocket accelerates through space. The key word there is accelerates. So that tells you that there is a force. Also, the force of the rocket is going to cause the rocket to move through space, and so there's a displacement. And the rocket's thrusters, which is causing the force, is what's causing the displacement. And so yes, there would be work done in the fourth example. This is also outlined on the physicsclassroom.com if you would like further detail or explanation. All right, so now that we know what work is, now we're going to calculate it. The formula we're going to use to calculate work is the one given above. Work is equal to F, which is force, times D, which is displacement, times cosine, and then that weird symbol is theta. And theta is the angle between the force vector and the displacement vector. But we're going to look at some examples so we can understand what I mean by that. Okay, let's first imagine that you have a tabletop, and on that tabletop you have a block. And you apply a force to the block to the right direction. Let's say it's 10 newtons. And as you apply that force to the block moves to the right 2 meters. What is the work done? What is the work that you do on the block? Well, we've seen from above that work is equal to the force applied, which is 10 newtons, times the displacement, which is 2 meters, times the cosine of theta. Now, what is theta? Well, remember, theta is the angle between the force vector and the displacement vector. Notice that the force vector and the displacement vector are both going in the same direction. And so the theta in that case is 0 degrees. So notice when displacement and force are going in the same direction, the theta or angle is 0. And if you take cosine of 0, this ends up just being 1. So that's why it's not uncommon for you to see the work formula just simplified to be work equals force times displacement. Okay, so in this example, what's my work? 10 newtons times 2 meters ends up getting me 20 newton meters, or in other words, 20 joules. Because remember, work is just energy that's transferred. So 20 joules of work is done on the block. Okay, let's do another example. Let's take that same scenario, but now what I'm doing is I've given the block a brief push, and now it's moving across the table freely, and as it's moving across the table, friction is acting on the block. Okay? The friction is going to oppose the motion. So if the block is moving to the right, friction will be facing to the left. And let's say my force of friction is 5 newtons. Now, I would like to know what work is friction doing on the block if the block moves 2 meters to the right. Okay, so now what we're going to do is we're going to use our work formula. Work is equal to the force applied, which we're wanting to know what's the work of friction. So that's 5 newtons, times the displacement, which is 2 meters, times cosine of theta. In this case, notice the vectors for force and displacement are still parallel, but they're facing opposite directions. So what is this angle? This angle is 180 degrees. So notice when displacement and force are opposites, the angle is 180 degrees. And cosine of 180 degrees is the same thing as -1. So my work is just 5 times 2, so 10 joules, but it's negative. And that makes sense. When you have friction acting against something, or in other words, when you have dissipated energy, the energy takes away from the total mechanical energy. So if you had this block moving across a table, the E dis would be 10 joules, or 10 joules is lost due to friction. Let's look at a few more examples. Let's look at an example where you have an object that's on the ramp. So let's say I have this block that's on the ramp, and I want to push the block up the ramp with a force of 10 newtons, and the block moves up the ramp 2 meters. What is the work done on the block? Work is force, which is 10 newtons, times displacement, which is 2 meters, times cosine of theta. What is the angle here? Well, you might be tempted to say, well, it's whatever the angle is of the ramp. Let's say, for example, 30 degrees. But that's not the case. Remember, theta is the angle between the force vector and the displacement vector. If you look at our two vectors here, they're parallel to each other and facing the same direction. So it's cosine of 0 degrees again, which means it's just 1. And so 20 joules of work would be done on the block. Finally, let's look at one last example. Let's say I have a flat surface, and I've got the block sitting on the flat surface, and I apply a diagonal force of 10 newtons that is angled at 30 degrees above the horizontal. And when I push, the block moves 2 meters to the right. What is the work done? Okay, the work calculated is going to be the force applied, which is 10 newtons, times the displacement of 2 meters, times the cosine of the theta, which in this case, the angle of the force vector and the angle of the displacement vector is actually 30 degrees. 30 degrees is the angle between the force vector and the displacement vector. So 30 degrees will get plugged into the equation here. Cosine of 30 is about 0.866 times 2 times 10 is going to end up giving us a work done of approximately 17.32 joules. If you would like more detailed examples of this, please make sure you visit physicsclassroom.com. Okay, a couple more things before we get into an example problem. Let's look at the figure in front of you. It says a 10 Newton force is applied to push a block across a friction-free surface for a displacement of 5 meters to the right. So the block is moving 5 meters to the right, and so there's my displacement vector. Now, the normal force and the gravity force, which are both 20 newtons, do not do any work on the block. And the reason why they don't do any work on the block is because what's the angle between the force normal and the displacement? It's 90 degrees, isn't it? And what is cosine of 90 degrees? Cosine of 90 degrees is equal to 0. So that's why there would be no work done on normal or gravity, because they both make a 90-degree angle with the displacement vector. So we can see that the work is only going to be done by vectors that are within the same plane. So the only force that will do work in this example is coming from force applied. So the force applied is 10 newtons, the displacement is 5 meters, and since they're both going in the same direction, that means my theta is 0, which means my cosine of 0 is 1. So my joules is just going to end up being 50 joules. So 50 joules of work was done from the force applied. Now let's look at another example. Let's take a look at an example where friction is involved. A 10 Newton frictional force slows a moving block to a stop after a displacement of 5 meters to the right. So as the block continues to move 5 meters to the right, with a force of friction acting on it in the opposite direction of 10 newtons, what work is done by friction? Well, the force is 10 newtons times the displacement of 5 meters, and cosine of 180 is negative 1. So that tells me that the work done by friction is negative 50 joules. So in other words, friction is stealing away energy by dissipating it. Let's look at two more examples. This example has a 10 Newton force is applied, while at the same time a 10 Newton frictional force is applied. The displacement is 5 meters again. So this is kind of like a combination of the first two that we just did. So we already know that the force applied does 50 joules of energy, and the force friction does negative 50 joules of energy. Now, there's a term that is called net work. This also means total work. So if I were to ask you what's the total work done on the block, the answer would be 0 joules. And that's because the 50 positive joules cancels out the 50 negative joules. All right, let's now go ahead and do some practice problems. A 3 kilogram block is given a push that gives it an initial velocity of 5.4 meters per second. How fast will the block be moving after it moves 3 meters if the coefficient of friction between the block and the surface is 0.14? Okay, we're going to solve this problem just like we've solved all the other energy problems. Only this time, instead of telling you that 20% of the energy is dissipated, you can now calculate the amount of energy dissipated from your work formula. So the first thing you always want to do is sketch a picture, which has already been done for you. After you do that, we want to draw our energy bar charts. Okay, so I'm going to draw two bar charts. The first one indicates the initial conditions. I'm told that it has an initial velocity of 5.4 meters per second. In other words, it has kinetic energy. Since the block is moving on a flat surface, there's no EG, there's no springs or any other deformity, so there's no elastic. The block definitely does not have chemical, and remember, we never put dissipated energy in the first bar chart. So that tells me all my energy in the first initial condition is all kinetic. Now, after the block moves 3 meters, it's still going to be moving something because it's asking how fast, but we know that some of it must have been lost to dis. So let's say EK is now a little bit less, and we have now a little bit of E dis in our system. Okay, now what we want to do is we want to figure out the total mechanical energy in the system. That's going to come from our first bar chart. Since all of my energy at the beginning is EK, I can calculate total mechanical energy by doing 1/2 mv squared. The mass of the block is 3 kilograms, and we're told that it's moving at a velocity of 5.4 meters per second, and then we will square that. So 5.4 squared times 3 times 1/2 gives me total energy of 43.74 joules. That means that the energy in the second pie chart must also equal 43.74 joules. So let's go ahead now and figure out what is the dissipated energy. Remember, E dis, or dissipated energy, is simply asking what is the work done by friction. And so that means we need to take the force of friction times the displacement that the block goes. We're already told that the block will go 3 meters, but we need to figure out what is the force of friction acting on that block in those 3 meters. To do this, we need to revisit our roots from semester 1. I'm going to draw a force diagram of this block. Since the block is 3 kilograms, that means that my force gravity is 30 newtons. Remember, you just take the 3 kilograms times 10. Since the block is on a flat surface, the force normal goes straight up, And since there are no other vertical forces, that means my force normal is also 30 newtons. There's nothing pushing the block, so there's no force applied, but since the block is moving to the right, force friction points to the left in order to hinder it. Now, if you remember from semester 1, force of friction is calculated by taking your force normal times your mu. The force normal we just found out is 30 newtons, and the coefficient of friction is given in the problem, 0.14. And so 30 times 0.14 gives us a force friction of 4.2 newtons. That is the force that we will plug in here in order to figure out our work. 4.2 times 3 is going to be 12.6, and since the energy of the force friction is facing the opposite direction of displacement, this is going to be negative. So all that tells us is that 12.6 joules of energy has been lost to dissipated energy. So that must mean EK is going to be the total energy, which is 43.74 joules, minus the dissipated energy, which is 12.6 joules. And so that ends up giving me my amount of kinetic energy of approximately 31.14 joules of kinetic energy. Finally, from this kinetic energy, we can calculate what our velocity is. Remember, kinetic energy is just equal to 1/2 our mass, which is 3 kilograms, times v squared. And if we divide by 1/2 and divide by 3 and take the square root to find velocity, our velocity is 4.56 meters per second. Finally, let's finish up the notes by tying up with one last concept, which is the work-energy theorem. And the work-energy theorem is actually a very helpful tool for us that we can use to solve for problems that involve changes in speed. The work-energy theorem states that the work net, or total work, acting on an object is equal to the change in kinetic energy. So if you can figure out one of those two values, you can figure out a lot of useful information. So let's look at a problem that ties that in. A bullet that's 5 grams is shot through a muzzle with a length of 75 centimeters. The muzzle is another word of saying the chamber for a gun. So we have a chamber, in which case the bullet is going to fire through, and that chamber, we are told, is 75 centimeters long, or in other words, 0.75 meters. The average force that will act on the bullet during this process is 4,700 newtons. How fast will the bullet be moving when shot? When I read this, I notice a couple things. I notice that it's giving me force at distance, so right away I'm thinking work, but it's also asking how fast, so I know I'm going to be dealing with kinetic energy. So on a test or a quiz, I'd be thinking of the work-energy theorem, which is work net equals change in kinetic energy. So let's write that out. Work net is equal to delta kinetic energy. Change in kinetic energy is really just saying this: the kinetic energy final minus the kinetic energy initial. Now, if you think about it, the final kinetic energy is going to be when the bullet leaves the gun. The initial kinetic energy is when the bullet, before it's been shot. If the bullet hasn't been shot yet, its velocity initially is 0. And that means this whole term actually just goes away. So now we've simplified it. We've said our net work is just simply going to be 1/2 m v final squared, with v final being the velocity as it leaves the gun. Now we've also learned that the net work acting on an object is going to be just the sum of the forces times the displacement. In this situation, we are told that the force acting on the bullet is 4,700 newtons over a distance of 0.75 meters. That's going to be equal to 1/2 the mass of the bullet times v final squared. Now the mass of the bullet is 5 grams, but remember it has to be in kilograms. So 5 grams is 0.005 kilograms. Remember, you move the decimal 3 places to the left. And now, if we multiply all of that together, we're going to get a v final of approximately 1,187 meters per second. This concludes the video on the work and work energy theorem.